Welcome back to Lesson 3, Example number 5, Part 2. And when we left off, we had designed for bending, for flexure, and we had got, okay, we're going to use a 6 by 12 because the modulus of the section modulus is big enough to get our stress under the allowable stress. I hope you followed that. That was not the most eloquent in the world, but to get our stress to be under the allowable, which is, let's go ahead and change colors here. Here's your allowable stress. And let's find out what our actual stress is now, since we picked a section modulus that's larger than the S-min, so it should be less than 1600 psi, which it will be. So let's go ahead and figure out the FB actual, let's call it. And we know that this is M over S, so we're going to do our actual, we have 12,000 foot-pounds times 12 inches per foot, and then we're going to use our actual S, which is 121.2. And our stress and bending actual, ACT we'll call it, equals 12,000, 1, 2, 3 zeros, times 12 divided by 121.2. And that gets us, and remember it should be less than 1600, and it is 1,188.1 psi. And that's good because that is less than FB, which is 1600. So we're good. And you might want to figure this out, your actual, because it may become handy later if you're doing if you have axial stress as well. So you do the stress and bending, in compression bending, because remember, not half of it. You have in bending, you have, if it's a positive moment, this is going to be in compression up here, and this is going to be in tension down here. So actually, you have some compression and some tension in bending. This is 1,188.1 up here, and this is 1,188.1 down here. And then if you add, you can look at, if you kind of flip it over and look at, there's your member, and this is your distributed load. And this is all in compression, if you're talking about bending. I mean, not bending, this is axial. This is F and axial, or sometimes they do it FT and FA, or FC, let's call it a force of compression, equals, remember we've done that before, is at P over A. So if you have compression, if you have an axial force and a bending force, you're going to have to add these together. So it's going to end up coming out, out like this. And it may come in and have a little bit of bending, or it may have a little bit of tension, but you'll have a lot of compression at top. And you have to add those two together. So this all will be compression, and then that little bit down there will be in tension. And that's if you have an axial load, which we do not in this case, so please just ignore that if you don't quite understand. Say, okay, you lost me, and that's all right, because that's just trying to explain it a little bit more about what we're looking at and engineering in general. So what we'll do is continue on, and what we want to do is check the shear and check deformation. Remember, we designed for bending. All right, so let's do that. And shear, if you remember, let's open another sheet here. All right, blank sheet, and we had, let's go ahead and write down what our stuff is here. We chose a 6 by 12, and it has a S of 121.2. Let's just start with that. 6 by 12. An S of 121.2 inches cubed. And then we also had an I of 697.1, 697.1. And that has an I of 697.1 inches to the fourth. All right. And we need to find, check out if it works for shear. Does this with a moment, actually, let's take out a moment and let's take we're going to need both of these. Our max moment was 1,200 pounds and our Vmax was 1,500 pounds. M was 1,200. That's foot-pounds. And our V was Vmax and Mmax was 1,500 pounds. All right, now we can continue and check what if it works for shear or not. And remember, there's the longer shear equation, and since this is a rectangular section, we can use the short shear equation, which let's just go ahead and change colors for the heck of it. So, actually, sorry about that. The stress of shear stress equals 3V over 2BD, or let's just say BA, and A equals BD. I'll put that up here actually. Get it out of the way. A equals BD. And I've said that before. And the reason I do that is because you can actually pull A off the list. So let's go ahead and go back to page 45 of your study guide, and the same place we got 6 by 12, we got the I and the S. Let's go ahead and put the A too, and I should have probably done that before, but no big deal. We can go back. 6 by 12, your area of your section is 63.25 inches, 63.25. And that's going to be inches squared. All right, now we can go ahead and figure this. We said 3 times V, which is 1,500 pounds, over 2A. 63.25 inches squared. And this is going to come out pounds over inches squared, which is PSI. So 3 times 1,500 divided by 2 divided by 63.25 equals 35.6, let's say, PSI. And let's go ahead and check that as well. 35.5, we're at 35.6, good enough for government work. And then so this is, remember we can do the same thing as last time. Maybe I should have done this ahead of time, but we're doing shear. We have capacity. And we have load. And remember, capacity is going to equal capital capital F, little v. That's shear stress capacity. What's the maximum shear stress it can handle? And then you have a little f. V usually figures out what is your load, your actual. So let's go over here, and FV, we need to figure out what is F. V, we just figured out. Little f, shear stress is 35.6 psi. And now we need to go back to our tables and figure out, hey, does this actually work for it? So we want to go back to page 44 of the study guide, and I believe the same place where we got the, what was it, the 1,600 pounds? Yes. Structural steel, or select structural, beams and stringers. You see F of B is 1,600, but we want FV. And you can see that's 85 if you go over. 85 PSI. All right, and as you can see is we are way under 85 PSI, so we are good. Good. And we move on. So let's go back real quick. You can say yes, check. Shear is good. You could do that if you want to. Now we're going to do deformation. How much is this going to deform? And you can go back to that simple beam, 2 equal concentrated loads, symmetrical placed equations, number 9. Go up to page 49. Remember, these are in your steel book as well. And we need to look at what the max, deflection max at center, so it's telling you that's going to be at the center, and equals PA, I'm going to have to, it's really small, PA over 24 EI, parenthesis, times, parentheses, 3L cubed minus 4 A something. Hold on, I'm going to look down. Maybe they have it somewhere else. There it is. They have it located over here as well. And your deflection max equals PA. Actually, they kind of messed with the equation. Let me go get my steel book. I will be right back. Actually, they do have it in the study guide. It is deflection equals PA divided by 24 EI, and then it's times 3L squared minus 4A squared in parentheses. And that's just, they put the parentheses stuff that was off to the right on the diagram there, and they put it over on top with the PA. So let's go ahead and use that equation here. Alright, delta equals PA 3L squared minus 4A squared over 24 EI. Alright, there we go. And it looks like P is our load again. A, again, once again, is 8. So let's go ahead and put these in and solve. Remember, we want to go down to inches. We want to change all this foot to inches. So we had P was 1,500 pounds. And let's always do pounds and inches. Let's just go ahead and change everything to pounds and inches. This is going to be kind of long. And you know what I'll do? I'll do what I typically do, is I will typically put this stuff over on the side just because it's easier for me to change this stuff on top. So A equals 8 foot times 12 inches per foot. Okay, so that's the PA over 24 EI. E, did we figure out E already? Let's go back here. E. No, we have not, so we need to go back to those tables. And E equals 1,600,000. And we got that on the lower table again, exactly where we got I, or not I, but FB and FV, I guess. So we'll go ahead and put that in. 2, 3 PSI. And then I, we already have, it is 697.1 inches to the fourth. Alright, then we have to figure out this part right here. And we say times 3, actually I always do this. 3 times L, which is, let's go back because I don't remember. 22 foot, is that this problem? No. L was 8 times 3 should be 24 foot. 24 foot times 12, that's inches per foot. Just conserve space, I'm not going to do that. And that's squared minus 4A was 8 foot times 12 inches per foot squared, and then we in parentheses. And let's go ahead and get all that out, and we get actual deflection. That's 1,500 times 8 times 12 divided by 24 divided by 1600, 1, 2, 3 more zeros divided by 697.1. I'm going to go ahead and get that, and then I'm going to multiply it by parentheses 3 times, parentheses again, 12 times 24, in parentheses squared, minus 4, open parentheses, 8 times 12, close parentheses, squared, close parentheses again, and I get 1.14 inches. Oh, and that is not good, because it is not less than 0.8 inches. It is not. So we can do this. It is not. No good. And you'll find that you actually have to go up to you could try a 6 by 14, and that 6 by 14 gives you an I of 1,128, and that will get you what you need. Go ahead and do that. All right, thanks.